Ajay has not only done this work, but he also helped to build the lab, set everything up, and set other people's projects up, projects that are going to continue for many years. So I'm very proud and very excited to see this presentation. And thank all of you for being here. And I know a lot of you have helped support him and supported me as we started. And so assuming everything goes well, Ajay also has accepted a position once he finishes here as a postdoctoral scholar at Stanford University with Taiwan once he completes this. So, anyways, Jay, take it from here.
Thank you so much, Dr. Garner, for such kind words here. Well, I'm not sure for those words here. But so let me just
no. Just the Twilight Zone.
Okay. So hi, thank you everybody. It's really nice to have you all over here. A very good afternoon to all of you. My name is Ajay Vikram Singh, and I'm a PhD graduate student at the University of Maryland College Park. And I'm going to define my PhD today, and the topic of that thing is a fundamental study of boundary layer diffusion flames. My honorable committee members include Dr. Garner, Dr. Kadu, Dr. Sunderland, Dr. Marshall, and Dr. Stars. So what I'm going to present is the work that I have done in the past 2.5 years. So these are the contents. We will be following the introduction, then I will be giving you the theoretical formulation that we formulated, followed by the numerical simulations. We made 2 different experimental setups, one for the free convection boundary layer diffusion flames to study that, and one for the forced convection boundary layer diffusion flames, and followed by the results and discussions, conclusions, major contributions, future work, and acknowledgements. Coming to the introduction. Boundary layer combustion has been previously investigated in connection with the various applications, such as ablative cooling, erosive burning of the solid propellants, as well as the surface combustion of the liquid fuels. The rate of flame propagation over any liquid or the solid surface and its ultimate growth to a large fire primarily depends upon the mass burning rate and the associated heat fluxes to the condensed fuel surface. The burning rate is also essential for determination of the flame lengths, fire growth, heat rates of heat release, etc. Therefore, a convenient method of applying a well-substantiated correlation that could permit the predictions of the local mass burning rates in such condensed fuel surface is actually very necessary. Also, differentiating the energy flux components at the surface of the condensed fuel surface has always remained a challenge for the researchers in the past. They have reported the heat flux components with a lot of uncertainties. So we tried to give up a new methodology that is based basically on this theoretical formulation so that we could accurately determine the various components of the flame heat flux, and we could differentiate between those. So the method that we propose here essentially has its basis in the Chilton-Colburn's extension to the Reynolds analogy, which essentially relates the heat, momentum, and the mass transfer in a boundary layer over solid or liquid fuel surface. So basically the equation 1 represents that, which basically essentially relates the heat mass and the momentum transfer. Tau S basically represents the shear stress at the fuel surface, S represents the heat transfer coefficient, M dot basically represents the mass burning rate per unit area. Mu, basically the kinematic viscosity, Cp, specific heat alpha, thermal diffusivity, G, mass diffusivity, and ln1 plus B, where B is basically the mass transfer number, the spelling number. Now, ln1 plus B expression comes here from the stagnant film hypothesis. Also, Emmons in his classical work, when he basically solved the forced convection burning on a flat pail and gave a similarity solution for that, he basically hypothesized that basically the shear stress at the surface of a combusting fuel must be proportional to the local mass burning rate. And he came up with this expression. That expression basically relates the local mass burning rates with the shear stress at the condensed fuel surface. So basically, essentially, if you can measure the velocity gradient at the surface of any condensed fuel surface, which is burning, you can essentially do the calculation for the local mass burning rate. So it's a very neat expression, very simple. It's oversimplified though. So the proportionality constant here depends upon the mass transfer number B. Now, also in a boundary layer, basically the heat transfer coefficient for the boundary layer diffusion flames can be approximated by equation number 3, where H is basically related in terms of the non-dimensional temperature gradients at the surface. Now, T star is nothing but T star is basically a non-dimensional temperature. N star is basically the normal direction to the normal direction in a direction normal to the fuel surface that is basically issuing fuel vapor. Now, utilizing equations 1, 2, and 3, we basically formulate an expression that essentially relates the local mass burning rates with the non-dimensional temperature gradients at the condensed fuel surface. Now, the proportionality constant here, C, basically depends upon B, Kw, and by Cp, where B is the mass transfer number. So this is a very neat expression. And it essentially relates the local mass burning rates with the local non-dimensional temperature gradients at the surface. So essentially, if we could be able to measure the local temperature gradients at the surface of a condensed fuel, we might be able to get the local mass burning rates. So my whole work has been basically to verify this relationship, whether it holds or not. So we have started with the laminar flames because they are much more stable. And this expression basically comes from the boundary similarity solutions. And so that would be easy to work with. So we started with the laminar flames. So what we did was that, after formulating this expression, we started looking in the literature. We started looking for the researchers who have reported the temperature profiles as well as mass burning rates in their papers. We could only find 2 papers. Boundary layer diffusion flames have been studied since 1950s, 65 years in past. Only 2 papers in which we found the total temperature profiles along the condensed fuel surface as well as the data of the mass burning rate. So what we did was that we took the papers, we extracted the data, experimental data, and we calculated the local temperature gradients with the temperature profiles. And we used our correlation, and we found that the mass burning rate that we predicted with our correlation actually comes out to be very close to what they have reported. The error was less than 10%. We got excited. So we started to do some numerical simulations. So these are the numerical simulations that we started to do in the ANSYS Fluent because I'm good at ANSYS Fluent. So, so we started doing that, and we set up the numerical modelers in order to study the forced convection boundary diffusion flames as well as the free convection boundary diffusion flames. So all the computational domain and the boundary conditions used in the model for the steady burning of the methanol and ethanol pool, we use 2 different types of fuels. We use methanol and ethanol in order to see whether there are effects of different fuels or not. And we started with the numerical solution. So all the boundary conditions have been studied. We validated our numerical models with the Hirano's data, Hirano's experimental data, and we found that basically our numerical model predicts the flame standoff distances as well as the peak temperatures quite accurately. So after validating the numerical model, we went on calculating the average mass burning rates in such flames, in the forced convection flames. So this is the data for the methanol forced convection diffusion flame stabilized at different free stream velocities. So these are the average mass burning data profiles. And we compared it with the experimental data, the Hirano et al., they come out to be very close. So what we found was that the average mass burning rate was found to increase monotonically with the free stream velocity. And that is normal, everybody knows that. We started doing that numerical simulation. So these are the flame stabilized in methanol and ethanol at lower velocities of U infinity equal to 0.5 meter per second. These are the flame stabilized at a higher free stream velocity of 1.8 meter per second. And what we see over here is that for the lower free stream velocities, what you see is that the buoyancy plays a lot of role. You actually get a second anchoring point, and that is due to the buoyancy. Basically, what it does is that basically it entrains the air from the domain exit, and it introduces some kind of a recirculating pattern, and that's why you get at low free stream velocities, you basically get a second anchoring point. And that is just because the inertia forces are not sufficient to overcome the buoyant forces. Now, at the higher flow velocities, you don't see the second anchoring point because the inertia forces totally dominate the buoyant forces. And this is how it looks like. So the temperature profiles from the condensed fuel surface rises from the boiling point of the liquid or the solid fuels up to the point to a maximum flame temperature, and then they will decrease into the ambient atmosphere to the ambient temperature. So this is normally how the boundary layer diffusion will look like. We started doing the velocity profiles. So these are the non-dimensional U velocity profiles that we have basically extracted from our methanol forced convection boundary layer diffusion flames that has been stabilized at U infinity equal to 0.5 meter per second. So why I'm showing you this is that because there is a very subtle difference between the boundary layer, non-reacting boundary layer, and a reacting boundary layer. In a reacting boundary layer, there is basically a velocity overshoot at the flame zone, well beyond the free stream velocity, and then the velocity basically decreases at the edge of the velocity boundary layer to the free stream velocity. Also, one thing of importance is there that at various stream-wise locations, starting from the leading edge of the fuel towards the trailing edge of the fuel, basically what you will see is that basically these velocity gradients actually decrease. So starting from the leading edge towards the trailing edge, these velocity gradients decrease. They exhibit the same nature as that exhibited by the temperature gradients. Similarly, the temperature gradients will also decrease from the leading edge towards the trailing edge. So why I'm saying that? Because velocity gradients are essentially the shear stress, right? Temperature gradients are essentially, so all these things are intrinsically coupled. Heat, mass, as well as the momentum, all these things are intrinsically coupled with these boundary layer diffusion flames. So we also plotted the fuel vapor mass fraction profiles. So these are the fuel vapor mass fraction profiles at different x locations for methanol bonded diffusion flames stabilized at U 20.5 meter at different streamwise locations. You will see that basically the fuel vapor mass fraction gradient is larger for the locations closer to the leading edge. And as we move away from the leading edge towards the trailing edge, that fuel vapor mass fraction gradient profile decreases. Similarly, at a particular x location, at a particular streamwise location x, basically your fuel vapor mass fraction gradient increases for increasing the free stream velocity. And that should happen because what happens is that as the free stream velocity increases, the flame comes closer to the condensed fuel surface, flame standoff distance decreases, and because of that, the fuel vapor mass fraction gradient actually decreases. So these are the free convection flames, which we did the summations. This is the methanol diffusion flame, which is at a particular time of 0.5 seconds. What we clearly see over here is that because if you see the temperature profiles, and you will see that there is actually a velocity overshoot. The velocity increases near the flame zone, and then it decreases back. And what we did is that when we started extracting the temperature gradients from all these numerical simulations, and when we plotted them alongside with the mass burning rate, the mass burning rate that we got from these numerical simulations, what we found was that there was a linear trend, there was a linear correlation, irrespective of the flow behavior, whether it be a force or the free convection flames, there was a free correlation. There was a linear correlation between the two. And we got a number. And this number we started calling as a magic number, because this number is nothing but equals to BK by CPL for a particular flame. So for this here, the BK by CPL for the methanol exactly comes very close to that number. And we after doing the numerical simulations, we found that basically the mass burning rate essentially follows this theoretical correlation. So
can I ask?
Sure.
Jim, go ahead.
Yeah.
I wondered how you chose your properties.
Okay, yes. So a lot of work, a lot of iterations, a lot of experiments, a lot of redoing of experiments ensure that we should calculate these properties at temperatures which we are going to tell you. We evaluated the K at the wall.
You're going to tell us.
Yes, I'm going to tell us. So everything. So we actually optimized this thing so that it should work for every fuel. We optimized it. So this was a lot of work has been there. It looks very simple. It's 1 year work. Just figuring out.
What is B?
Yep.
I missed what B was.
B is the mass transfer number or the Spalding number. So it's basically the ratio means how much the heat is being liberated by fuel to how much is being, is required for the vaporization of the fuel. So basically, it's just a ratio of that.
Like the droplet burning
Yeah.
theory.
May I ask you?
Sure.
So do I understand correct that the mass burning rate here is the computed burning rate in your
Yes.
model, right?
Yes.
And the temperature gradient is also from the model, right?
Yes.
What is your boundary conditions on the surface of the model?
So what we did?
Thermal.
Oh, sure. So the boundary surface, how we actually did it at the interface, we basically created a Mars source here. So the gas phase was solved in a decoupled manner than the liquid phase. But at the interface, we use interface boundary conditions. Time base was based on the energy balance of the whole thing. So based on the energy balance, we created a Mars source. So just in order to make sure that the liquid fuel film is always there at the interface.
Well, my question then is, weren't you expect a perfect line here? Because if you calculate your mass balance, which is right there,
Sure.
based on the temperature gradient, which is right there in the model,
Sure.
and you saying that they are linearly deviated in your model,
Sure.
why isn't there is a perfect line in your data?
So I will tell you why there isn't a perfect line in the data. So you see these points, which is not lying there, right? This is what is your concern, right?
Well, you have. I'm
It's-
saying
it's-
saying what you're showing here is a linearity. You're forcing in
Yeah,
the model.
it's not forcing. It's actually a linear relationship. It's not forcing. It's actually a linear.
Well, you prescribed it, right?
No, I didn't prescribe that. That's the idea.
Each of the symbols is a CFD simulation.
So again, these are the
So
CFD simulations.
each symbol is a CFD simulation.
Yes, but
so-
in the CFD simulation, it's prescribed that
No.
the gradient is equal to the burning rate.
So the mass burning rate, see, that interface condition was only used to create a mass source at the interface. After that, the mass burning rate was calculated by using the ρS as well as the Stephen mass transfer velocity. No way the mass burning rate calculated by that method would have coded in this manner. We didn't use that boundary condition because ultimately, if you started using the boundary condition, you will almost get a linear trend, But we didn't use that. We just use that to create a fuel film. That's it. That's the mass source. And then the gas phase is solved in a decoupled manner. Now, how the mass burning rate is being calculated? It's being calculated by rho s into Vs. Rho s is basically the density of the fuel surface, as well as Vs is basically the normal velocity component, the Stephen mass transfer velocity. And you multiply both, you will get the local mass burning rate. This is the fuel blowing velocity. It has been calculated by the fuel blowing velocity. So the blowing velocity of the fuel has ensured the calculation of the mass burning rates. This has not come from the boundary conditions. If it would have come from the boundary conditions, this whole thing will be a flop. So it will not work.
Just to follow. Go ahead.
Yeah.
No, I still don't completely understand it, but go ahead.
But just to follow up on Stas' question, so rho s and Vs are rho s Vs are produced by your model. So how does the model know what to make rho s and Vs?
It doesn't know what to make rho s Vs. It just solved the Navier-Stokes equations for the reactive boundary layers. It doesn't know how to make rho s Vs. It solves them, and then what you get, that's what you the values take. It is not dependent upon the boundary. It is not dependent upon the interface field field conditions.
There has to be a coupling. So you do not specify rho s and Vs.
We didn't specify
the
rho s
model
and
has
Vs.
to figure out.
No, model has to figure out. We didn't specify.
So what's the model to figure out rho s and Vs?
Navier-Stokes equation.
Yeah, conservation of energy.
Conservation is equations. Conservation.
Well,
But you
if
don't
if
specify
it's
the
an
energy,
energy,
everything's
but that's a boundary
Yes,
condition.
that's
It's
what
a
I'm
boundary
saying.
condition
Yeah.
that
if
is
it's a conservation
substituted.
analogy, it's a perfect
The
line.
condition is slip walls, non-slip walls.
Yes,
That's
So-
all.
but then there's an energy balance, right?
The energy is.
Energy balance.
Right?
Yeah, that's the
Yeah.
thing actually.
Yeah, there's
It has
energy
not
balance.
been calculated by the energy balance. It has been calculated by rho s and the Vs. What we get after solving the the continuity equations and the momentum equations. So you get those values, rho s and the Vs. So after you solve it, so the only boundary condition that has been applied is for the interface. Where the liquid fuel film is there, in order to create a mass source just to maintain that liquid fuel film there. That's it. And that mass source has been created based on the energy balance.
Well, but that means that you dictated by the energy balance. And the energy balance is right there.
Yes.
Right, that's.
But then we didn't do the calculation. Oh, yeah.
So in the interest of time, we'll continue this and the
Yeah,
closed
so-
session
so
after.
I will be able to, because actually this was one of the questions, from one of the people in the past as well, and I think I will be able to give you an answer.
Yeah. So we'll move on to the experimental results, which
So coming to the
Batch.
pre-convection boundary layer diffusion flames, we started building up a setup. We started building up a setup for the pre-convection boundary layer diffusion flames. And this is what the setup looks like. It's very simple, So we place the whole setup on a load cell in order to measure the low average mass burning rates. So we put up a insulation board, and basically we have a 8 by 8 centimeter of the condensed fuel rate and that insulation board. And we drilled holes at several locations so that we can also measure the heat fluxes in the fluid. So what we do is that, and we take up a Velmax 2-axis traverse mechanisms, mounted a thermocouple, and we basically do the grid scanning of the temperature profiles. We measure the temperature profiles in such pre-convection boundary layer diffusion flames. And so the condensed fuel wick is basically an insulation board, which we is 8 by 8 centimeter. We bake that wick for around half an hour, and when we saturate it with fuel, we saturate it with around 90 ml of the fuel for the pre-convection flames, and then we burn it. So this is the measurement plane. So we have taken all the temperature data in the center of the plane because the width, the temperature variations along the width of the sample were found to be not that great. They were almost the same. So we measured the temperature profiles at the center, and we did the grid scanning fashion, and we mapped the whole boundary layer diffusion plane. So this is how the setup looks like. So basically, we have a condensed fuel wick that is burning. We have a thermocouple Velmax XY slides. Now, the Velmax XY slides were controlled by stepper motors, which is basically integrated. The stepper motor controller was then integrated with the library. So we automated the whole process. We automated the whole process in order to do the grid scanning of the temperature profiles. Now, let me talk about the challenges here. Now, when we started using the condensed fuel rig, the problem is that it only burns steadily for only around 450 seconds. That's it. It doesn't burn more than steadily because it starts to begin to dry up, and then the mass loss rate is basically it tries to reach a plateau, and then it will start decreasing. So basically, we only wanted to measure during the steady burning regime time. That means where the mass loss rate was actually constant, that slope was constant. So basically, we have to map the whole temperature profiles for boundary layer diffusion flames within 450 seconds. So that's why we automated the whole process, so that it's easy and so that we can map the whole temperature profile of a particular boundary layer diffusion flame within that time period of the steady burning. So what we see over here is the front and the side view for an entire boundary layer diffusion flame. And this is the thermodynamic video what we use with the Velmax traverse mechanism. So all the temperature profiles, basically the thermocouple measurements that we have done is basically they have been compensated for the radiation corrections. So we compensated the radiation corrections. We incorporated the radiation corrections in the raw temperature profiles. We use a classical expression from the Collison Williams with the Nusselt number correlation in order to account for the radiation corrections within such frames. And we found two equations. We got two equations and two unknowns, and you can solve those equations, and you can basically account for the radiation correction in such frames. So these are basically the radiation correction as well as the raw temperature data profiles at the leading edge as well as the trailing edge.
Jay, what did you choose for the second unknown?
Which unknown?
Well, you said two unknowns.
Two unknowns.
Right?
One unknown is basically the gas temperature Tg, and one unknown is U, Captain, the velocity. So basically, you get the velocity as well.
Good.
So these are the temperature profiles in the free convection modular diffusion flames. So this is a methanol, ethanol, as well as the PMMA. In the PMA, we didn't do the temperature profiles near the leading edge because it was very intensely bubbling there. So we started it from x equal to 1 centimeter, and we made the complete temperature profile. So what you see over here is basically that the temperature increases from the condensed fuel surface, which is basically at the vaporization temperature of the fuel, to some maximum flame temperature, and then decreases somewhere downstream towards the free stream. So when we measure the condensed fuel surfaces, the temperature remains approximately at the boiling points of the liquid fuels. However, in the case of the PMA molten surface layer temperature actually varied. So we basically did some measurements at the surface temperatures of the PMA, and we found that basically the PMA molten layer temperature decreases rapidly as we move from the leading edge towards the trailing edge. So the temperature actually decreases from around 708 Kelvin to somewhere around 650 Kelvin. So this is how the temperature, molten layer temperature of the PMA surface will decrease. So
Ajay,
yes.
The figure, the leftmost figure,
Yes,
and then
leftmost.
the figure to the right. So are these which temperatures? No, leftmost figure here, all the way to the end.
Mhm.
Right, and so you've got a nice profile in Y.
Sure.
And then what about the profile right next to it? Is that, yeah,
this is for ethanol.
I get that. But you've got a gas, you have
Yes.
your gas temperatures, and you have a Y here. But what is this profile that you're showing? Yeah,
For this profile,
Yeah.
so this is the leading edge of the fuel surface.
yeah,
That is the trailing edge of the fuel surface.
yeah, I got that. And then what about right next to it? That's your?
You're
that's
talking
just a
about the
content-
color bar?
That's just
Just
a
a
content,
color bar?
Okay.
Yeah,
This color
so
bar?
just the legend,
So
so
this is
you
the
know
legend.
what the temperatures are.
This is the legend for the temperature contours.
Okay, and then you measure surface temperatures,
Yes, we measure the surface
and
temperatures.
do you show those? I know
Yes,
you
I will
mentioned,
show you those.
you mentioned
Yeah,
that
I will show
they're
those.
close to the boiling.
Yeah,
Okay.
so I will show those. So this is basically the PMA molten layer temperature. The liquid fuel surface temperature also we have plotted, So the graph is there in the thesis, but I don't think so we have it over here in the slides, but we have plotted that, So we have measured both. So at the condensed fuel surface as well as the, we measure the temperature of the real. Now coming to the experimental results for the flame stand-up distances, so we also measure the flame stand-up distances. We measure the flame stand-up distances by two methods. One was the visual, in which we use a side DSLR camera, side view flame photograph. We measure the flame stand-up distances, and also we got the flame stand-up distances with the help by noting where the peak temperature is actually located along the y direction. So we basically do it by both methods. So that is why one visual is basically by the side view photographs which we process, and the experimental data is basically just by the pulse measurements. So what is important here is that if you see that the non-dimensional flame stand-up distance in both the methanol and the ethanol phases are almost proportional to x raised to power 1/4. That means it follows the boundary of scaling rule. However, in the case of the PMA, it doesn't follow the boundary of scaling rules. It is basically it is x raised to the power 1/3. And why it doesn't follow the boundary of scaling rules, I will be talking about that later when we are going to present the other results. So coming to the temperature, yes.
So you have this x to the 1/4 power, and you say it follows the boundary layer scaling rule?
Similarity.
Okay, so I'm just wondering why the standoff distance would follow a boundary layer scaling rule.
It is going to follow.
But why? It's not the boundary layer, right? It's a flame standoff.
Yeah, so it's like a flame standoff. It's going to be like like the thermal boundary layer divided by 2, right? Thermal boundary layer thickness divided by 2, right? If you do-
Possibly,
Yes.
it depends upon what would be
Possibly, yeah.
driving
So
the
for-
boundary layer
Sure,
thickness,
sure.
because it could, you've got a couple of different important velocity scales.
If you solve the boundary equations like the constant movement and Williams, when they basically essentially calculated the flame stand of distances from the similarity solution following the basis solution, and they calculated for the free convection flames, it actually follows the boundary scheme. They showed that. That was a classical paper that basically essentially shows that the flame stand of distances for the free convection boundary diffusion flames actually follows the boundary scheme. And it has to follow the boundary scheme.
Yes. Okay. I'm with you. I'm wondering if it's possible to have a different velocity scale besides the one associated with, for example, your boundary. Okay, you got natural convection, right?
Sure.
And then you've got forced convection, right?
Sure.
So I'm wondering, how do you know which scaling you're going to follow? Because you could follow a scaling associated with your forced convection, or you could follow a scaling associated with your free convection. And I'm not sure that you're going to get x to the 1/4 power for both of those.
Yeah, for the forced conversion, it will follow a similar other rule. It will not follow the x raised to power of 1/4.
Okay.
For the free conversion, it is.
Okay.
And the forced conversion will be x raised to power 0.5 actually.
Okay.
So these are the normal non-dimensional temperature gradients that we basically extracted from our thermal profile data. So these are the non-dimensional temperature gradients for the methanol as well as ethanol. And on the figures to your right, basically represents the non-dimensional temperature gradients for the VMS surface. What we found is that the temperature gradients actually decreases right from the leading edge of the fuel surface towards the trailing edge of the fuel surface in both cases. And that should happen because the film stand of distances actually increases from the leading edge towards the trailing edge. So the temperature gradient has to increase from the leading edge towards the trailing edge. Also at a given streamwise X location, and then we calculated the, we used our correlation in order to calculate the average mass burning rate with the help of the average temperature gradients that we extracted from our data. And we were measuring the average mass burning rate through the load cell, which is basically the measured one basically represents the average mass burning rate represented through the load cell, because we were using the load cell to measure the average mass burning rates. And this is the average mass burning rate that we got from using the correlation. So after extracting the average temperature gradients and the fuel surface and using the correlation, we found that the mass burning rates by both the things, they come out to be real close. So the error was less than 15% in all the three cases. And these are the B numbers that we use for that. So the close agreement in estimating the average mass burning rate by using the theoretical correlation and by using the data measure with the load cell suggests that given correlation works quite well in estimating the average mass burning rates. Now, after estimating the average mass burning rates, we also wanted to know how well it correlates with the local mass burning rates. So what we did was that we used the theoretical results of the Kim et al. So we used the theoretical results from Kim, and we just plotted that for the methanol 8 by 8 centimeter burning surface. And this is our methanol experimental data that comes out to be. So it comes out to be very close. Now, initially what happens is, when we have not optimized the transport properties and at what temperature we should calculate, it was a little bit off, but then we optimized it, so it came out to be very close.
And you're getting the local
Yes.
mass burning rate?
Yes.
Experimentally?
Yes.
How do you do that?
By the local temperature gradients. By using
Okay.
Assuming metal transport.
Okay,
Yeah.
okay, so
Yeah.
it's an estimate. It's an
So-
estimate.
Right.
So
based
it's an
on-
estimate based on the
So it's like
non-dimensional.
developing a tool. Can you use the gas phase to know something about the
Yeah.
solid phase while it's happening?
So this is the local mass
Condensed phase.
Just a clarification.
Sure.
The B number you're using is the purely convective B number.
Yeah, we use the purely convective adiabatic V number, So,
Yeah, so everything's just from fundamental properties. There's no tweaks, because otherwise you could just tweak it.
So also this is the methanol numerical data that we got. So this is the methanol numerical data that we are getting. So it also comes down to be very close. These are the theoretical results for the ethanol, the black dots that you see, and these are the ethanol experimental data. So the ethanol experimental data actually overpredicts the local mass burning rates, as proposed by him. And this is basically the pitch, and this is how we get. So basically, what essentially I'm trying to show here, what the point that I'm trying to prove here is that that essentially, if we are able to measure the temperature gradients at the surface of a condensed fuel accurately, we can extract the local mass burning rate profile. And it comes out to be very close to the theoretical model. So that means it is a way to actually experimentally determine the local mass burning rate. You know? So we can use that, and maybe we can extract the local mass burning rate to that. Also, we burn solid fuel PMMA in order to challenge us further. We started burning the solid fuels, and we use PMMA for that because PMMA burns clean. It does not form char. So we started using PMMA measurements, and if you look at the surface of the PMMA after burnout times at different burnout times, you will see that it has regressed before the origin of the request. You will see a valley before that, you know, and you know after a long period of burning, you will see a valley starts forming in the PMMA surface. And these are the regression profiles for the PMMA surface, as well as the time average regression rate. So basically, we burned the PMMA for fixed intervals of time. We let the sample cool, cut down from the middle, and then try to measure what is the surface has regressed. And this is the regression profiles. And we basically did the time average regression rate based on how much regression divided by the total time of burning. So basically, you get the regression rate. So what we see is that the significant regression was observed in the leading section when compared with regression locations downstream. Regression rate increases with time in the trailing section due to increased heat feedback with time and slow intensity condition in this section. So essentially, these are due to the edge effects actually. If you start looking at the trailing edge, you will find that for the increased burning times, basically the regression rate actually increases.
So Ajay, in doing this calculation, do I understand correctly that you make assumption that I take a piece of PMMA, I heat it up to 700 Kelvin, and then cool it down? The density of resulting piece will not change. Is that the assumption that is incorporated in this calculation?
Come back again.
I take a piece of PMMA, I'm going to put it in the furnace, and I'm going to uniformly heat it to 680 degrees here. That's close to decomposition, but not quite. Then I'm going to take it out, cool it down, and measure its density again.
Okay.
Will it change according to this?
So we have taken the constant density. We are not taking.
Try it out of curiosity.
Yeah. So we are not taking the changes in the density. We are only taking the constant density.
Yeah. What is a little bothering is that those changes are like a very layer where those things.
Maybe it may change. It may.
Anons had done some work where they did that and used some data for the cast PMMA, not for extruded. And it's a negligible effect when they did a similar measuring the regression.
The cast certainly also does that. I mean, the bubbles in PMMA formed way before the actual muscles occurs. So the PMMA swells, and it never, when you cool it down, it never comes back to its original shape.
Well, they had showed that it does, but
so maybe So maybe there might be density
another
variations
error.
we didn't account for that. You know, we only take the constant density variations. You know, so that's why this is also a method. You know, you to estimate the local mass burning rates. That's why we say that our method is better. So
Do you account for that swelling or burnout when you're actually measuring that
we
temperature
don't.
gradient?
We don't.
Right, but you took a temperature gradient.
Yes.
You used the saying it's at this exact position I measured that
Yes.
temperature. You use the stand-up distance off of that, but it's shrinking and expanding as that's happening. So
it might be
might not be
expanding.
the
Yeah.
location
So
of the
maybe
surface.
after cooling down, you know, so after cooling, there might be thermal expansion during when it is hot. You know? But when it cools down, you know, that thermal expansion we are not accounted for that. How much it would be, how much it would not be. We are not done that. So that's why this is just an expression, you know, just to calculate the regression.
No, I think it's talking about the movement of the surface as you perform your
yeah, you
temperature
incorporate the
measurements.
regression.
Oh yeah. That's the regression.
You
of
have
surface, of course, yeah. So that's why. Okay, so I think
Never mind.
I will explain that. So then we measure also the mass burning rate at the PMMA surface can be approximated by a posteriori which was given by Piezo, you know. So basically using the density as well as the regression rate profiles at two different times divided by the total time, we can get the local mass burning rate. And then these are the results, you know. So these are the measured, which was based on the regression rate profiles. These are based on the temperature gradient profiles. They don't match them very well, but they are pretty close, you know. And of course, this is because this is the regression rate profiles. There might be due to the changes in the density or might be some other reasons. So this is how it looks like. So I would like to skip this slide because this is all already in the videos. So heat fluxes in the producer zone. So then we started measuring the heat fluxes. So what we did is that, you know, because since we know we have measured the local mass burning rates at each location of the condensed fuel surface, you know. So we can basically extract the net heat flux out of that by just multiplying it with the effective heat of gasification. Since we are measuring the temperature gradients at the condensed fuel surfaces, we can extract the effective heat flux out of that. And we are measuring the temperatures at the surface, so we can basically extract the radiation heat flux from that. So we can easily calculate the radiative heat flux by just doing this simple energy balance. So this is how the convective heat flux would look like in such ways, And this is the basically by using the crude approximation, because this crude approximation is being used by the researchers, So they have approximated the convective heat flux by K delta T by YF. YF is basically the flame standoff distances. So how the crude approximation relates. So it gives pretty good here, but it just doesn't do that well over here.
So how do you get the flame radiation?
So the flame radiation, because since we are measuring the local mass burning rate, m dot, so we are getting the net heat.
Okay.
Okay.
Got you.
So everything else we know because we are measuring that. So we can just do the calculation. So this is the surface radiation from the surface. So basically for the liquid fuels, the radiation from the surface is very small. However, for the PMA, it's quite a lot.
But your m dot double prime is an integral measurement, though, right? It's local.
Because you did the
That's right.
regression. Yeah,
Yeah,
that's why it's local.
It's local.
Yeah.
It's local.
It's local. Your m dot double prime is local
It's local.
from
The temperature measurement.
Temperature measurement.
that. Okay. So,
Okay.
but that's an estimate of m dot double
Yes.
prime.
That's
But you
that's-
have an integral measurement, and then based upon a profile that you're assuming
Sure.
works, you're getting these additional profiles.
Sure.
I just, yeah, get this. It's not, I mean, there's no, your assumption is that your temperature gradient gives you m dot double prime, but you're not measuring m dot double prime independently.
Well, we also
Locally.
did from the regression locally, but only at a resolution of 50 seconds, right?
Okay, so
Is by
are,
burning them at different amounts of time and
And-
measuring the regression.
are you using, so which,
That's what he showed earlier, so he had,
so
they're slightly off, but they follow the same trend.
So which M dot do you use here? The
Yeah,
one you
that's
measure or
it.
the one you use by temperature? So if you use the temperature one, then you're using on the left for your M dot.
Yeah.
So
You're using on
here
right
the
for
m dot is
regression.
basically the temperature.
that's,
But
yeah,
you also
okay,
have
which is
the
okay.
regression that comes off of that temperature.
So this is the
right?
temperature.
So
So
now you have two terms on that
see, in
same
order to be
temperature.
confident that what we are doing is correct, that's why we validated against the theoretical model.
That's, I mean,
And that's why they have come out to be very close. So there's no reason for me to believe that they might be giving totally.
no, I mean, I think the trends are okay. Yeah.
So and this is how we are getting the flame radiative flux now. So for the PMS. So basically, essentially,
In
what
the model, you don't have radiation though, right, of any kind?
in the model, yes. So this is the experiment.
Right, I understand.
Yeah.
But it just goes towards the validation.
So these are the idea is that we can actually basically do the calculations for all the components of the flame heat flux by using this methodology. And so these are the average heat flux that we basically average it out. So basically for methanol, ethanol, PMA, and in all the cases you will see that the convective heat flux is basically around 85% of the total incident heat flux. So these are laminar, steady, small flames, where convective is the dominant mode of heat transfer to the condensed fuel surface and basically paralyzes the fuel.
How large are your plates? Just to remind us, how large are your plates? How large are you burning? How tall your boundary?
Yeah, what's L? That, I'm thinking,
Yeah,
8 centimeters.
8 centimeters.
8 by 8.
centimeters.
and just.
So for the fake shade by 8
I
centimeters.
have to ask that question.
Sure.
But I mean, so I'm wondering,
Mhm.
have you thought about what happens to all your scaling laws as L changes? So in other words, let's say you did
Mhm.
100
Sure.
centimeters. Okay.
So how it is going to change? Yeah.
Yeah. So
So I will come back.
Okay.
I will come back. Everything will be answered. At the end.
Everything will be-
Conclusion section. That's fine.
Yes.
Why do you use the temperature data to get the mass flux in that equation? Why wouldn't you use the regression since it's independent?
So regression data can be used for the PMA.
Right?
So-
Why you can't use it for the.
So we can. So why I use it, because the temperature gradients when we compare with the data with the load cell, because we were also measuring the data, the mass loss rate with the
If
load
you
cell.
go back to the Reynolds analogy,
Mhm.
would it hold for radiation?
Reynolds analogy, will it hold for the radiation?
That
It might hold for the radiation as well. So basically, the Reynolds analogy actually works for the turbulent.
only competitive.
So it might. So because see, what happens is that Reynolds analogy is basically it holds very well for the laminar flame, for the laminar boundary layer as well as for the turbulent boundary layer. It holds. It holds.
That's true.
That's true. It holds. It holds. So basically, the Reynolds analogy will hold if your dP by dx is equal to 0.
And
Your Prandtl number is equal to 1.
you can predict convective heat flux in
So
both
sure.
cases, but
So-
not radiative one.
So yeah, so maybe, so that's what means. I'm going to answer every means these are the concerns, whether it is going to work for the large scale fires, whether it is going to work for the flames which have totally radiation dominated flames, whether it is going to work, it will fall apart, So the answer is I don't know, but I will give you exactly a very, very, very good explanation in the end why I think it might work. I will give you an explanation for that. So we also measure the convective heat transfer coefficients. Convective heat transfer coefficients can be represented in terms of the non-dimensional temperature gradient. So if you are measuring the non-dimensional temperature gradients, you can measure the convective heat transfer coefficients. So basically, these are the measured convective heat transfer coefficients for both methanol and ethanol PMA. And this is from theory. Theory is basically for a vertical flat plate, heating of a vertical flat plate in a free convective environment. And basically, you can approximate by using the flame temperature, and then you can measure the transpose properties. So theory doesn't predict very well for the case of the PMA, but it does come out to be very close for in the case of the methanol and ethanol data. And this is basically H measured by the crude approximation. The crude approximation is basically H can be related in terms of Kf by Yf, where Kf is basically the mean film thermal conductivity and Yf is basically the flame standoff distance. So basically, the crude approximation doesn't give you, it actually over predicts the convective heat transfer coefficients.
But,
So we,
but again, it depends what you pick for K.
yes. K is basically the mean film temperature, basically the average of the flame and the wall temperature. So yeah, it will. So I picked basically the mean film temperature. So basically the average of the flame and the wall temperatures. Now, if somebody else will pick K something else, he will get something else. So it depends.
But don't, in your thesis, you do state that you pick it at the surface of the fuel.
So that is
that's
something that is for calculating the local mass volume.
Why is it
So
different here?
This is K delta T by YF.
But
delta T is,
but you base part of your derivation of your formula including this includes this one.
so that is the measured one. That is what we are measuring. That is the measured one. That H measured. That is what is calculated from there. That is basically
What I'm asking you is why you pick out the
This one?
KW different ways for two different calculations. For your general correlation, you
Sure.
pick KW at the surface, and here you pick it
Sure,
as the mean.
I totally get it. I totally get your answer, your question. So basically, this is what comes from. Basically, this comes from the normalizing the bundle equations. H as a convective heat transfer coefficient in terms of the non-dimensional temperature gradients, where K has to be at the wall. Okay. Now this comes from the crude approximation that we normally the researchers do. H is basically H delta T is equals to K delta T by YF, where K delta T is basically T flame minus T wall divided by YF. YF is the flame standoff distances. So K has to be evaluated at the flame temperature because you're taking that. That is the thickness that you're taking into account. So this is basically the crude approximation. So that comes from there. So it has to be evaluated at the K film. That's what I think it has.
But film temperature is not a flame temperature.
Film temperature is not a flame temperature, definitely. It is the mean of that flame.
Yeah,
flame
and the crude approximation
not.
that has been done
Yeah.
before
So
doesn't work anyways.
I'm not saying F doesn't mean the flame temperature. F here means the film temperature, which is basically the average of the flame and the wall temperatures. So I'm not saying we are evaluating K at the flame temperatures. We are evaluating the mean film temperature. Mean film temperature is basically the average of the flame and the wall temperatures. So this is the local Nusselt number that we got, so this is actually X by KW, so basically you got the Nusselt number. So what you will get is that you got the experiment and the ethanol data, and then we compare it with the theory, So for the ethanol experiment, we come out to be very close. For the PMA, it doesn't follow that much. We also did some plume thermal analysis. So we measured the temperature profiles as well as in the plume. Why we did the plume thermal analysis? Because this was not a part of our study because we were trying to make a wind tunnel for the forced convection by the diffusion films, and our blow was to be shipped from Germany, which took around 4 months. So we did the plume thermal analysis in those 4 months. So we did the plume thermal analysis. So what we see is that as the flame, as you go towards the plume, what you will see is that the flame starts coming back to the wall. So basically, the maximum temperature increases monotonically with increasing height along the wall. The position of the maximum temperature moves closer to the wall in terms of Y by X as X increases. And then we did, because we are using a total heat flux gauge to measure the total heat flux, we were measuring the temperature gradients at the surface so we can get the convective heat flux. We are measuring the temperature surface temperature so we can get the re-radiation heat flux. So basically, again, by doing that, we can get the various components of the heat flux. So here, again, the fluid approximation, Q flame convecting can be SKF, which is basically the K equivalent to the mean flame temperature, which is basically the average of the flame plus wall temperature. T flame minus T heat flux gauge surface, because the heat flux gauge surface is basically cooled by cold water. So you have to take into account the temperature of the heat flux gauge surface divided by YF. YF is basically the flame standoff distances. Now, if you don't measure the flame standoff distances correctly, you will not get very good approximations. It may vary a lot, depending on how you are doing it. After doing the free convection flames, for the laminar free convection flames, we started doing for the forced convection flames. So we try to test this methodology basically in the forced convective environment as well. And we said that whether this methodology breaks down for different flow conditions or not. So we started building up a setup. So this is how the forced convective setup looks like. So we have a wind channel in which an ABM pass variable speed blower blows air. It pressurizes the plenum. It then forces the air through a converging session through a set of honeycomb and the turbulence reduction springs. And we get a very uniform velocity profile at the outlet. We place our fuel sample right after the outlet of the wind channel. And we map the temperature profiles with help of the thermocouples mounted on the Velimax X5 slides. So we made this amazing wind tunnel. I'm very proud of this. So it does very, very good work. Why I say that it does very good work, because at the regions of the interest where you place the fuel sample, the turbulence intensity is less than 1.5%. It gives you, and it's very repeatable. It's very repeatable. So, and we started building that, started doing some more experiments, and we started studying the turbulent boundary diffusion frames as well for a while, and for experiments as well as for the. Mine is very much laminar regime. I'm not going into turbulence. I'm just measuring them. And these are we totally characterize the wind tunnel outlet. So basically, we characterize the velocity profiles and the wind tunnel outlets. Also, we characterize that for the turbulence intensity levels. And we found that what we see is that we get a very uniform velocity profiles at different freestream velocities. As you increase the speed of the blur speed, you will get very, very, very repeatable and very good uniform velocity profiles at different speeds. So we use a Deltec Dynamics hardwire anemometer for doing that, and we measured the whole. We characterize the whole. Outlet of the laboratory screenmeter. So we exactly know what is coming out. So we exactly know what is actually.
What's the maximum velocity?
5 meters per second. 5. It can go from 0.5 meters per second to 5 meters per second at increments of 0.1 meters per second.
I think it can do more. We tried to slow it down.
Yeah.
We're purposely slowing it down.
Yeah. So these are the experimental results for the average mass burning rates that we measured through the load cell. So as we all see that basically that average mass burning rate increases monotonically with the increase in the free stream velocity, and that is what is happening here. And we got good data. These are the results for the average of 5 tests. The repeatability error for the methanol case, I think, is less than 2%. So, and these are the flame stand-up. These are the total flame lengths. So actually, the flame length also varies. So basically, as you start increasing the free stream velocity, basically the flame length of the fuel, the flame length also increases. Monotonically with the increase in the free stream velocity. So this is the data for the methanol, ethanol, and different. So we chose only 4 representative velocities. We use as 0.8 meter per second, 1 meter per second, 1.5, and 2 meter per second. So this is how the boundary layer diffusion flames under first flow look like. So these are the above data is basically for the methanol. So at U equal to 0.79 meter per second and U equal to 2.06 per second, you again see a second entry point here for the methanol flame, as we have seen in the numerical simulation results as well. And for the ethanol, you don't see a second anchoring point here because it occurs much later. So it happens around 9 centimeter over early, so you don't see here. And at the high fluid velocity, you don't see a second anchoring point. And this is just a PMM flame. For the PMM flame, it was found that it used to occur the second anchoring point only intermittently. It doesn't happen all the time. In order to explain that, we basically did the Richard number analysis. So basically, we calculated the Richardson number. The Richardson number can be calculated by the formula given above. So delta T here is basically being fed by the T flame minus T wall. And you can use this analysis. And what we found that when the Richardson number was less than 1, for high free stream velocities, basically the inertia forces dominated the band forces, and then you don't see a recirculating pattern at the domain axis, and that's why you basically get no second anchoring point. But when the Richardson number was greater than 1, that means the bind forces are totally dominated. And when the bind forces are dominant, so what they do is that because of the buoyancy, what it does is that basically it's entering some air from the outside, and it basically creates a recirculating pattern. And that's why you get a second anchoring point in these such things. So these are the temperature contours and the profiles for the force flow frame. So we have got methanol, ethanol, and the beer vinegar. So at different flow velocities. So they look almost the same as a boundary diffusion flame would look like. So basically, it increases in the normal direction to certain flame temperature and then decreases somewhere away from the surface. So these are the temperature contours and the profiles that we got for methanol, ethanol, and the BMA. And again, we see what we see here. So there's a lot of data. If you start reading in between the lines, there's a lot of things that you can actually understand just by looking at the graphs, qualitative. That's it. The temperature gradients are very high near the leading edge, and they started decreasing. Also, the flame, which was very thin near the leading edge, starts increasing in thickness somewhat. That means as you go away from the leading edge towards the trailing edge, the flame actually begins to thicken. It starts to thicken, and that's what you can see from the profile. Just by qualitative. It's not qualitative, just by qualitative. So the flame peak temperatures, how they're flame peak temperature actually increases monotonically with the incoming free stream velocity. So as the free stream velocity increases, your flame peak temperature actually goes on increasing. So basically, at a high flow velocity, your flame peak temperature will be the highest.
Chief, how does it compare with adiabatic flame temperatures?
So
like in stoichiometry?
Sure. So for the PMMA, the adiabatic flame temperature is around 2495, right? So
yeah, a little less than that.
Yeah, 2493, 29494, if you do the calculation for the adiabatic flame temperature.
I would say a little less than that. Less than that. 22.
2494.
In Celsius, though.
No, it's in Kelvin.
Yeah.
2494 in Kelvin. So PMA flame temperature is 2494 in Kelvin. I've done the calculation. So 2494 Kelvin, if the PMA flame temperature is there, if you measure it, it will only go up to 1950 Kelvin. For the methanol flames, the adiabatic flame temperature is 2150 Kelvin. It will only go up to 1950 Kelvin. The maximum I'm talking about after doing the calculations. So the flame stand-up distances when we measure it, So for the methanol as well as for the PMMA, what you see over here is that the flame stand-up distances actually start to follow the modular similarity rule again. Now the power law exponent has changed. It has changed from 1/4 to 1/2. So this is how it is following. So these are the laminar flames. They have to follow that. If it doesn't follow, that means something actually we are doing it wrong because it has to follow it. If you do the calculations for the similarity solutions for the boundary layer, even for the reactive flow, you have to get that. There's no way that you will not get it.
So but I still, because you have, I'm looking for the possibility where it's not going to follow a scaling associated with the conventional laminar boundary layer because you have a you have a complication, which is buoyancy. So could you imagine that the complication would impact the scaling?
Okay. So I forgot to tell you that we only did from 0.8 meter per second to 2 meter per second. Okay. Now within that range, it actually falls. If you go towards the lower free stream velocity, actually the whole thing blows up. Why it blows up? Okay. Because as the number goes to 0, boundary layer thickness will be infinite. Okay.
So another point I just want to make here. So have you considered, because your wall normal length scale is in fact the standoff distance, have you considered normalizing your temperature distributions by that length scale instead of L?
We actually did the non-dimensional temperatures, but we have not checked this.
Right, because you've got all of these profiles, they all look the same. They're just all stretched out. You showed it a few slides ago, slide 67.
Yep. Okay. So so we have not tried that. So maybe we can try that as well. Yeah. Sure.
There is a similarity for both problems.
For free and the forced.
Yeah, there is. Yeah.
And also, what we did was that when we plotted because we were calculating the non-dimensional temperature gradients, and we were calculating the average temperature gradients and the average mass spreading rate to the load cell, and then we tried to put it on graph paper. We found that they do behave in a linear fashion, though the fit is not that good. Maybe this point is off. But even if you fit it with a line, you get something very close to what you will get for the PK by CPU for that field. So a linear relationship exists between the average mass spreading rates and the non-dimensional temperature gradients on the field surface. And the non-dimensional temperature gradients, they behave in a linear fashion. So These are the experimental results for the non-emission temperature gradients that we got for the methanol, ethanol, and the PMA at two different free stream velocities. So the non-emission temperature gradients at the fill surface is higher than the leading edge, and basically the lowest at the leading edge. Also, the temperature gradients at each stream-wise location increases with the increase of the free stream velocity. Basically, if you go for high velocities, basically the temperature gradient increases because the frame standoff distance becomes lower. So these are the PMA regression and the local pyrolysis rate. It is exact the same analysis that we did for the free convection flames. So basically, we measured, we burned down the PMA samples at definite intervals of time and allowed the samples to cool, and then measured the surface regression profiles. And it almost exhibit qualitatively almost the same behavior, as those are the free convection flames. Now, the important thing that I want to point out here is that, we also did some temperature measurements in a PMA surface, near the leading edge at x equal to 6 mm from the leading edge. And what we found that if you start making the temperature measurements at different times, your temperature profiles actually changes, because the PMA is actually the surface regresses with time. And since the surface regresses with time, basically the flame, there's a moving boundary effects. And because of that, you will see that the flame temperature actually decreases as you go on increasing the time burnout time. And also the flame standoff distances actually increases. This basically what will happen is that, with time, your incident heat flux to the PMA surface at the leading edge, it is going to change a lot. That means it is not going to be steady at the later times. The gas phase is only steady at a very small burning regime time. That means up to t equal to 150 seconds, it might be steady. And after that, the gas phase may not be steady because this is how the temperature profiles change with time. Similarly, for the filling edge, when we did that, x equal to 80 mm, what we did is that, what we found that for higher burning out times, what happens is that the flame started moving with the surface. Now, one thing more I want to present it over here, for higher burnout times, your flame standoff distances actually becomes increases. One might expect that the PMS surface is regressing. The flame should move with the surface, right? So the flame standoff distance should decrease, right? But in the leading session, it doesn't happen. Why it doesn't happen? It doesn't happen because you form a valley. Because as you start burning the PMA, you form a valley, and that valley basically the flame doesn't keep up with that valley formation. So essentially, after time t equal to after a long burn of time, actually the flame standoff difference increases. But in the training section, what happens at long burn of times, the flame actually follows the surface and actually moves closer to the surface. So it actually follows the regressing of the surface, and actually the flame standoff distance decreases. Though the temperature gradients, they do not change much here now. But if the flame standoff distance is increasing, and if the temperature gradients are not changing, that means the convective heat flux is not changing. So what is the increasing? I think the radiative heat flux is increasing here. And that's why.
What do you have upstream of the leading edge in your experiment? Nothing or a plate?
A plate.
So there is an inert plate.
Inert plate. So these are the experimental results for the local mass burning rate. So we plotted the experimental results. The experimental results here means that we actually calculated from the non-emission temperature gradients, and we use the theoretical solution for the Amund's. So Amund's theoretical solution can be represented by the equation 1 above, and we compared the data. So the comparison doesn't look that nice, but it does follow the same trend, and they are very close. The errors are not much. Even for the ethanol case, it does follows pretty nice trend, and the errors they are happen to be small. So that means, in a way, if we start measuring the temperature gradients, it can give us a very good estimate of the local mass burning rates. And it is an experimental value because we are measuring the temperature gradients, and it is dependent upon that. And so we can extract that thing from there. So these are the local mass burning rates for the PMA. Now, the PMA, we measured the local mass burning rates by the 3 methods. Now, the first method was our method, which was based on the temperature gradients. Second method was based on Amund's solution. And third method was based on the regression data profiles. In all the 3 cases, they come out to be close. They are not so off. So, though if we use the load cell data and if we use our method performs much better than the 2 methods. Similarly, now, if we can measure the local mass burning rate, we can actually measure the shear stress, local wall shear stress of the surface as well by using the Amund's hypothesis. That means by just relating them with the B number and the unitary, we can just extract out the shear stress of the surface. And so we extracted out the local wall shear stress for all the 4 flames, for the methanol, PMA, and ethanol, and for the different velocities. Similarly, you can measure the combustion coefficient. So combustion coefficient is nothing but the non-dimensional mass burning rate. So it has been represented by the equation above. Now, if you measure the local combustion coefficient, you can what was a thing of satisfaction in the end was that in the range of the free stream velocities between 0.79 to 2.06 meters per second, the average value of the product, the average of the combustion coefficient multiplied by the non-normal raised to power half, is obtained as 0.85 and 0.93 for ethanol and for methanol and ethanol, which comes out to be very close what Emmons has included for his experiments actually. So when he calculated these things, they come out to be very close. So now using the local heat fluxes, we are doing the same thing. We are just so this is the net heat flux, convective heat flux, fluid approximation, re-radiated heat flux on the surface, radio. So basically, what we have done is that we have not used any heat flux gauges. We have only used the thermocouples, and with the help of the thermocouples, if I can get the huge lot of data, and it's a good estimate. It's not that bad estimate, because when we compare with the values with the values that has been put in the literature, they come out to be close. They're not that off. So it can be viewed as a technique that can basically do some simple measurements and get a. So this is what we have been focusing. We also measure the convective heat transfer coefficient. So convective heat transfer coefficient and normalizing the Barlow equations and with that expression. And then we compare it with the crude approximation. The crude approximation is basically based on the fifth level difference. And what we see is that the crude approximation doesn't use that values. That crude approximations, because there are so much uncertainties associated with that, because just correctly, what temperature is correctly, flame standard distance is correctly, and then at what temperature you should evaluate here. So that will include a lot of uncertainties. So in the end, so this is the functional form of the Nusselt number. So this is what we derived now from the Emmons solution. So the functional form of the Emmons solution, and we approximated. So this is just for the laminar frames where the convectivity is that basically the dominant mode of heating. We have neglected radiation. So we are guilty of that, but we have neglected. So we have neglected the radiation. You can form a nice expression for the local Nusselt number, and you can calculate the local Nusselt number by plugging the values for the flame temperatures, the wall temperatures from the experiments, and you can get this nice expression. So Nusselt number being written with the root or EX, and then you can compare it. Means how your data actually compares with this thing. So these are the non-dimensional flame stem normalized flames. So black line is basically the Emmons solution that you get. So Emmons solution is basically this one. So these are the things that you get. So this is just from the Emmons solution that we derive, right? And this is the black line that you represent here, because the normalized flame standard distances would be y by x is equal to 1 by any x. So basically you get this line. And this is our flame standard measurements, So all the data that lies, So it doesn't agree that well, So it is a way off, at the top. But there are so many approximations involved in deriving this thing over here, because we have totally neglected the radiation. We have simplified it, and so many approximations are involved. So that's not a bad. But for the PM wave, as you look, the data, experimental data, comes very close to the Emmons solution. It starts coming out to be very close. Simply, if you look for the local Nusselt number, without a root REX for the methanol and the ethanol flames, So the black line is basically the Emmons solution in both the graphs. And these are basically our experimental data profiles, which we calculated the local Nusselt number from our experiments. And what you see over here is that as the free stream velocity increases, basically the flames tend to be much more coming towards they tend to follow the Emmons solution, much more. For the lower free stream velocities, because the buoyancy plays a role, and because of those buoyancy effects, the data is somewhat off, But for the high free stream velocities, where the buoyancy doesn't play as much role either, they come out to be very close. So these are very steady conversions, and they agree well for the high free stream velocities. Similarly, this is for the PMA. Even for the PMA, you get the same thing. For the high free stream velocities, basically, they start following the Emmons solution pretty well. We also looked at the transient local Nusselt number for the PMA. So in the PMA, because based on the regression data profiles, you can basically calculate the local Nusselt number based on that, and you can approximate it by this thing. And what you see is that at different burnout times, the data has been flattened. with the amount solution. So what you see is that as you go on increasing the burnout time, the data actually starts deviating from the amount solution. That means the flame is only steady, maybe can be thought of being steady only at the shorter burnout period times, because at the shorter burnout period times, your gas phase is actually steady. As your time increases, your gas phase is not steady anymore. It goes into a transient phase. So you have to make all the measurements within 150 seconds window. That means you have to repeat a lot. You have to burn a lot of POA sheets. You have to basically use a lot of funds from your advisors to do that. So this is what happens. So
that's happening because the surface is regressing.
Because of the moving boundary effects. Right. So and similarly for the flame, at a high burnout time. So as you start increasing the burnout time periods, it basically starts deviating from the amount solution. So it only agrees very well for the burnout times of short periods. Conclusions. The results from the present study show that there is a unique correlation between the mass burning rate of the condensed fuel surface and the local temperature gradient of the fuel surface. The given methodology works well for both free and the forced convection boundary diffusion flames and is capable of giving reasonable estimates of local mass burning rates and heat fluxes in such flames. The theoretical correlation agrees with the methanol, ethanol, and PMA forced burning data to within 15% accuracy. Using the proposed correlation, the various components of the flame heat flux can be appropriately deconvoluted. Based on the experimental results, the convective heat flux in such flame is relatively high and contributes approximately 80 to 90% of the total heat flux. These are the small laminar steady flames we are talking about. So we also have discussed the shortcomings of using a crude approximation for the determination of the convective heat fluxes, which doesn't do a very good job if you're not doing it correctly. And it will depend from researchers to researchers because they all tend to use different transport properties for calculations. While the burning rate correlation is based upon laminar assumptions, it is hypothesized that this technique should follow a similar form for turbulent burning of a flat fuel surface, albeit with a modified functional relation which must be experimentally determined. The Reynolds analogy is basically valid for both the laminar as well as the turbulent burning fuel flames. So the Reynolds analogy, it will become valid, it will remain valid until unless your dP by dx is equal to 0. If your axial pressure gradient is close to 0, it's negligible, it is going to hold. If it is not, it is not going to hold. Also, it will hold when your Prandtl number is close to 1. If your Prandtl number is not close to 1, you have to basically introduce the corrections for the Prandtl number from the Chiltern-Cohn expressions, and then it is valid for a wide range of Prandtl numbers. So we would like to believe that this thing will actually escalate to the turbulent boundary diffusion flames as well. But in that thing, when the flame becomes turbulent, what happens is that it starts forming soot. If the flame becomes large or it becomes turbulent, it will start forming due to the because the maybe due to some zones which will be richer. So basically, so it will start forming soot. Now, when it starts forming soot, what will happen is that basically the radiative heat flux of it will increase. Now, our methodology doesn't take into account the radiation. It only takes account only the convective heat flux. So it might break down at those large-scale fires where the radiative is the dominant mode of heat flux. So what are the major contributions? By extension of the Reynolds analogy, a new methodology is proposed for estimation of local mass burn rates. The proposed correlation is capable of accurately determining local and average mass burn rates and modular diffusion flames, irrespective of flow conditions, geometry, and different fuel types. A new methodology is proposed for the estimation of local heat fluxes in such flames. The methodology is novel in the sense that it allows the determination of the various components of the flame heat flux by simply knowing the local temperature gradients on the surface. The proposed burning rate correlation is based upon laminar assumptions. It totally neglects it neglects the radiation. Turbulence needs to be incorporated as most fires are turbulent, and our correlation so far has only been applied to the laminar cases. Further research must be taken to study the effects of the grid-generated turbulence on the proposed burning rate correlation. The theory upon which the burning rate correlation is based neglects radiation. Inclusion of the radiation effects in proposed correlation is actually desirable, and further research must be taken in order to do that. Now, having said that, let me conclude with this thing. If we start looking at the work of Ahmad and Faith basically did his work in 1978, right? So Ahmad wrote his thesis in 1978. So if you start looking, his turbulent burning rate correlation, mass burning rate correlation for the turbulent as well as the laminar fire groups, it is based on a convective scheme either. It is also based on the convective scheme. It neglects radiation altogether. But when Ahmad tried to use his burning rate correlation for all kinds of the data available in the literature for very large-scale fires. For example, that the fires that the experiments that have been done by Orloff and Uris, And when he started doing that, what he found that his burning rate correlation predicts really well the mass burning rates, even in such flames which are radiationally dominated. Why there was such a happy circumstance? Why this was such a happy circumstance? They didn't know the answer for that.
Logarithmic scale.
That's
the key. You plot your data on logarithmic scale, and then it predicts things really well. But if you look really crazy, you find that there is factor of 5 to 10.
So maybe, but their mass burning rate correlation that basically predicts the data actually comes out to be very close to the mass burning rates that has been proposed by them.
Not for what I see, but
yeah.
Good.
So this is what they said in the thesis. So my
It's a good correlation.
yeah, it's a very good
Gather
correlation.
in the data,
And
they identify what the radiation fraction is for the different fuels.
yeah, so basically it actually works very well, with the radiation dominated cases as well, And so who knows? Maybe for the radiation dominated cases as well, if we introduce some radiation factor, it will work as well for that case as well. So that was the thing, and I would like to thank my advisor, Dr. Gorman, for giving me an invaluable opportunity to work on challenging and extremely interesting tasks. I would like to thank all the committee members for their invaluable time, and for going through my thesis. I would like to thank Professor Elaine, because she has been a mentor, guide, advisor, and friend for such a long time. And I feel very privileged and honored to have worked with Professor Elaine. And I would also like to thank Professor Struve, Dr. Brugg, Dr. Bala Kumar Balachandran, Dr. Kofinas for giving me the future faculty funds for traveling to conferences. And I would also like to thank all my colleagues in the Fire Protection Laboratory. I would like to acknowledge the financial support for this work from the Winter Market Foundation of University of Maryland, College Park. So, thank you. Thank you.
Great. So you can see that there's a lot of work that was in there, and I think I deleted 30 slides of work from your earlier PowerPoint. So there's a lot more. So because I know the committee is going to have a lot of questions, I'd like you all, if you can, to hold those questions, let the public ask some questions, and then we'll all have everyone else adjourn and do those privately so that we get out before 4 o'clock. So does anyone in the audience have questions for Jim?
So when you have like for instance, one of your graphs that has the X star on the X-axis and the temperature gradient on the Y-axis, right? And so you have an expression that is a prefactor, another term, and then the exponent close to 1/4, right? The that prefactor, is that something that has to be experimentally determined for every fuel?
Which prefactor?
I wish I should
For your
have done.
correlation, you have X power quarter.
Okay.
And there's a number before the X. Is that experimentally measured or is
It will come to the experimental measurements. It will depend upon the experimental measurement, but it should follow the boundary experiment. That means that exponent has to be, it will depend. That's a good question actually. To be very frank, yeah, it will depend. It will come from your experiments. So whatever you measure, it will come from experiments. But actually, X raised to the power half or 1/4, that has to be good. Right. Your prefactor will change.
No, I'm just talking about
will change according to the landscapes. Right. It will change according to the landscapes.
You started off by the Reynolds or Holborn analogy, but if you look at the solutions by Emmons or by Ahmed and Faith, they'll use the Swamp's elements variables.
Sure.
Doesn't your premise fall out just from that? That the temperature gradient is related to the burning rate? I mean,
You end up with slightly different expressions, but it's very similar.
It has to be the same.
Yeah, it's not the same.
It's not the same.
I guess that's my question. You
No,
end up with
Lewis-
the expression that is
if you
slightly
say
different.
the Lewis number is equal to 1, it has to be the same.
So expressions end up to be different.
Pardon?
Expressions end up to be different than what
No,
this.
I don't know. I can't imagine that it would be different. But the way you choose your properties is very important.
Sure.
Obviously, because you have a real problem there.
Sure.
And,
So actually, yes.
That kind of guidance to give to people is
Sure.
very, very useful.
Sure. So that's what means we started using the transport properties. We are trying to follow the work of the Kim, Diris, and Grosser, in which they basically formulated the theoretical expression for the free convection burning on a vertical flat plate. So basically, they calculated all the properties of the wall, right? So they calculated all the transfer properties of the wall. Just Cp, the specific heat, they calculated a very, very flame temperature.
Who did that?
Kim, Diris, Grosser.
Oh, okay.
Yeah, John has a nice
so we
explanation
followed
of
that
why he does it.
Yes. So when we start, so we were actually trying to figure out which transport properties to include it, because if you start using different transport properties, it will change the results.
Anyway,
So we optimized that.
really good job.
Thank
So
you.
Very impressive.
Thank you.
Very much.
Anything else from the audience? Isaac.
For this plot of the earlier ones on free flow, you showed a picture with 10 different flux gauges where you also measured these fluxes. How does that actually compare to your estimates of what you think this total flux is going to be? Some of those end up being kind of low. The figure you just had up before it went away 30 times wider, the same one for free flow. Just the free flux profile is a function of normalized distance from the base of your sample going up from 0 to 1, which is 0 to 8 centimeters. The total heat flux that you see at the top of those samples, I think, is kind of low compared to other ones that I've seen. But I didn't see a comparison between what you got by backing that out off your temperature measurements and your estimates by using your mass flux and L versus what you actually measured with your heat flux gauges. So I wanted to know if you looked at that, because you showed those gauges.
So we didn't compare, so we didn't measure it with the heat flux gauge in the pyrolysis zone because we were using the liquid fuels. And for the PMA, we didn't do it either, because PMA, the problem is that, if you start, the problem is how you're going to measure that in the case of the PMA. Because it's bubbling and everything, it will cover the surface and everything. We only use it for the plume, that's it.
Right,
So
so
the
then
heat flux
right
gauge-
at that boundary, right above your sample, where you have temperature measurements going to the top of that sample, and then gauge right above that, how do those two compare?
So we didn't do exactly right on top, but at least some distance away in the streamwise direction. It was separated by around 1.5 inches or 2 inches, something like that. So basically what you see is that, basically it increases a little bit, at the trailing edge, it increases actually as you move toward. Why it happens is because the flame starts coming back to the wall, and that's why the flame intimately touches the wall and everything. And you get a sharp increase, and also there is a no blowing effect. When the condensed field surface is not there, there is no blowing effect. The blowing effect actually decreases the heat flux a lot. So
Is that region turbulent?
that region, no, it's not turbulent. It's still not turbulent. It doesn't look like turbulent.
Because that second anchoring point occurs after the end of the sample, slightly, and that's where that jumps.
So even if you see the plume, the plume doesn't look like it. I mean, you get very, very, very steady measurements. It doesn't look like turbulent.
But you could, because you have
Yeah.
m dot double prime f now integrally, it would be easy to calculate a Grashof number in order to determine what, how close you were to transition.
Definitely. Yeah, that I can.
Yeah, and at some point we did that.
Yeah. So
the Richardson
actually-
number analysis.
actually, I was not going to do this plume measurements at all because our blower got shipped around 4 months later. So we thought, let's do something. So we did this experiment. That's it. So I was not interested in the plume. I was only interested in working this whether it holds or not. So
Okay, so Wawa, you have the last question from the audience.
yes.
Yeah, I was wondering, in your experiment, are all the flames inside the boundary layer, or did you do something to make sure the flame in the boundary layer?
Inside the velocity boundary layer, actually.
Also naturally?
So maybe only for the lower flow velocities, if you start going for 0.5, we only chose the free stream velocities when you approach briefly. We chose 0.8. We're starting from 0.8 to 2 meters per second, and in that case, it was approximately inside the boundary. Because the thermal boundary layer thickness and the velocity boundary layer thickness will depend upon the Prandtl. Okay, so if the Prandtl number is equal to 1, they will almost be equal to each other. Right?
Yes, but I just want you to appreciate that that is true, assuming that your transport properties are kind of governed by the wall, but you've got buoyancy, which changes things. Okay?
So yeah, that's what it means. So we didn't choose very low free stream velocities. So otherwise it would have, it would have not, even the non-analogy would have not.
For all these tests, at least over the fuel surface, then it was all in the velocity boundary layer, though the plume you could see some of them kind of transition there. But we didn't take measurements in those regions. So all the regions that we measured were where it was within, but there are clearly, and that's why we limited. We didn't go to very low ones.
We didn't go to very low ones.
So in the interest of time, thank you very much for coming. Thank you, Ajay. And you're all welcome to grab some goodies on the way out. And then if you excuse us, we'll just have a little committee time to resolve some more of these questions.
Yeah.